Hello everyone, this is the Algebra 2 end of course review for Chapter 2, and we will be focusing on quadratic functions. Here's the good news. Transformations of quadratic functions is the same as it was in Chapter 1. So one more time, if you are going to move a function up, you will add an amount to the function. If you are going to move it down, you're going to take away. If you want to move it to the right, you are going to subtract from the x. If you want to move it to the left, you add to the x. If you want to reflect over the x-axis, you multiply the entire function by -1. If you want to reflect it over the y-axis, you're going to only change the x variable. If you wanted to shift this thing or stretch it vertically, you're going to multiply either by something greater than 1 to stretch it. And if you are going to shrink it, it's going to be multiplied the entire function between 0 and 1. Now I have added function notation in Chapter 2 just to kind of get you used to it. We have used this before, but it is exactly what I just said. Adding to the function moves it up, subtracting from the function moves it down. Adding to x moves it to the left, subtracting from x moves it to the right. -1 times the end function is going to move it over the x-axis. Negative times just the x is going to reflect it over the y. If a is greater than 0, it's going to stretch it vertically. If a is between 0 and 1, it's going to it's going to shrink it vertically, and then of course the horizontal and the compression and stretch. For you to be able to use these transformations, you need to be familiar with the quadratic parent function. So the quadratic function looks like a smiley face, and it starts at 0, 0, and it is symmetric about the y-axis, and the domain continues to go forever to the right and forever to the left, so the domain is not restricted, but just like the absolute value function, the range is restricted. As you can tell, the range only exists from 0 to positive infinity. So domain is left to right and the range is up and down. Let's go ahead and talk about properties of parabolas. So a parabola has an axis of symmetry, just like an absolute value function. It's going to go straight down right through the middle of that vertex, and this is vertex form right here. Vertex form of a parabola has an A, it has an H, and it has a K. K is what shifts it up and down. H is what shifts it left to right, and A is going to be either a stretch or a shrink, and if A is positive, it's going to be smiley. If A is negative, it will reflect, and it will be a frowny face. The axis of symmetry is going to be a vertical line right down through the vertex, so all you have to do is say x is equal to whatever your horizontal translation is. So if I was going to give you a very specific example, I can tell right now that this is going to be a smiley because that is a +2 and it is going to stretch it vertically. I can tell that this has been moved to the right 2. So if it's moved to the right 2, the origin will be at 2 and it will go up 3. I meant vertex, not origin. So if it's got a vertex at 2, 3, that means your axis of symmetry is going to go straight down through that 2 on the x-axis. That is your axis of symmetry. Next, we have intercept form. So you still have a little A here where you can tell whether it's been reflected or not, or stretched or shrunk, but you have x minus a solution here and a solution here. It is literal factors, okay? So if you wanted to figure out your axis of symmetry, what you do is just take the average of where it intersects your x-axis. So if it says x minus like 3, you know what? Let me just write an example over here. So let's say you have a -3, and then you have x plus 5, and you have x minus 8. I don't know, something like that. Well, let's make it easier. Let's put 7 here. All right. So I can tell right now that that's going to be a frowny face because that's a -3 and it's going to be vertically stretched. I know that it's going to hit my x-axis at -5 and it's also going to hit the x-axis at 7. Those are solutions. If I wanted to find the axis of symmetry, all I would do is just add them together, divide by 2. which gives me 1. So if I was going to graph it, that is going to be equal to a positive 1 right there. Well, the only problem is that you can't tell what the vertex is just by looking at that form. You can tell that x is equal to 1, but you don't know what your y value is going to be. You're going to have to go back in and you're going to have to plug in that 1 and simplify. So I have a -3 times 6 times -6, which is going to be -36 times -3, which gives us positive 108. So that would be the vertex. They could ask you whether or not it has a maximum or a minimum, and that very heavily depends on if it's been reflected or not. If it's not been reflected, obviously you're going to have a minimum value for your vertex. Minimum values are going to be your y value of your vertex, not your x. If it is a maximum, same. It's going to be the y value of your vertex if they ask you for the max. So once again, right here, I just kind of reiterate that you're going to wind up with the axis of symmetry, and you're going to have a vertex. But in this one specifically, this one is standard form. It's not written on your notes, but you can go ahead and write it here. This is standard form. This is typically what you want it to look like if you wanted to factor or if you were going to do something like the quadratic formula. So everything is going to be equal to 0 if it is in this standard form. If they ask you the axis of symmetry, you're going to use the formula -b over 2a, and the c will be your y-intercept. Oh, you got standard form right here. I wasn't even paying attention. All right, solving quadratic equations. There are 4 ways that we reviewed this year on how to solve a quadratic equation. We can either factor it. If you factor it, you do need to set it equal to 0, and there are many different ways to factor. 2, you can graph it. If you have access to Desmos, go ahead and graph it. Look at the x-axis. That's where the solutions are going to be. 3, you could use quadratic formula. That one works all the time. It's helpful if you're not able to factor or graph. And then 4, you can use square roots only if you don't have a linear term. Sometimes when you have square roots, like if you have maybe like x plus 3 squared equals 16, this would be ideal for square roots. You can just take the square root of both sides. But then whenever you take the square root of both sides, you got to remember that you have to do a positive and a negative. So the square root of 16 is going to be positive -4. If you subtract 3, you're going to wind up with -3 plus or minus 4. You will have 2 answers when you solve quadratic formula or quadratic equations. So in this case, it'll be -3 plus 4 is 1. -3 minus 4 is -7. If you were going to run a quadratic regression with Desmos, it's going to be the same as in Chapter 1. You're going to go to Desmos, click on the plus sign, enter your table of values. But you do have to type in a lot more in your formula. It says y1 and then tilde, a x1 squared, and then you have to do b x1 and then plus c. But this time it's going to give you a, b, and c because it is in a quadratic regression, and it will give you something in standard form. The only other thing that we talked about in Chapter 2 is a system of equations. There are 3 different possibilities that you can have if you are given a system. You can have like a quadratic and a linear that do not intersect. If they don't intersect, you're not going to have a solution. If they intersect at one spot, you'll have, of course, one solution. And if they intersect in 2 places, you will have 2 solutions. The easiest thing for you to do is go ahead and type them into Desmos and see where they intersect. The only thing I do need to warn you about, let's say that you have a linear equal to a quadratic in this form. You're going to want to graph this in one line and graph the right-hand side on the second line, and then you need to see where they meet. If you type it in as it is, I don't think that the Tennessee State Desmos site will allow that. So type them in separately in different lines and find out where they intersect. Okay, let's take a second and read this. It says the function f of x represents the distance in miles a helicopter is from a launch pad over time. So f of x is the distance in miles, and it says X would be the hours after takeoff. So just from that one sentence, it says that X would be in hours after takeoff. So I'm going to look to see which one has hours for takeoff. These two do not. They do not match the description, so I'm going to mark out A and B. This one says if the maximum speed of the helicopter is 250 miles an hour, what is the best that represents the appropriate axes? So if you look, it says the maximum it can go is 250 miles an hour. So if you can see here in this choice C, after 1 hour, it appears to have traveled over 400 miles. So this one is impossible, making D the only choice for this question. Next up, it looks like we have a system of equations that is already graphed for us. So if it's graphed for us, all we need to do is look to see where they intersect. So it looks like it intersects here and here. You will not, I repeat, do not look at the x-axis. That is only when you have a single function, not a system. So it looks like I've got a solution here at -4, 0. So C is out. And then the other one is at -7, -6. So A and D are out. It has to be choice B. Notice how this one is a no calculator question. Very typical question, especially if it's already factored. So immediately what you're going to do is you're going to write the factors equal to 0. It's been a while since we've talked about something that has x squared on it. That's going to give you 2 solutions from that. If you add 9 to both sides, look what happens. You have to take the square root of both sides, and when you take the square root of both sides, you have to do a positive and a negative. And then over here, you just have a single answer because it's just x. So if you look, I should have 3 answers. That means B is out, D is out. You have to have a positive and a -3 and a -6. A has a -6, C has a +6. So C is out. Next question is going to test your skills with transformations. What we're trying to do is we're looking for the student that has correctly transformed the function. So you're going to start with this function right here, and we're going to double check and make sure that each of these function notations matches its description. Well, according to this, you see how they're subtracting a 1? That would actually move your function right 1. That is not what they say. So student 1 is out. This one right here looks like we are multiplying the entire function by -1. That's going to reflect it over the x-axis, but it says y-axis. Student number 2 is out. This one, you are subtracting 3 from the function. Subtracting 3 is going to move that entire function down 3 units, and it does say we are moving 3 units down, so it has to be student 3. And we're going to talk about why the last student is incorrect. This one says +4, but you're adding 4 to the x. So adding 4 to the x is going to shift it to the left 4 spots. It says 4 units up, which is incorrect. Okay, so I already have this one worked out for you. It gives you a table of values, and it is asking you to find an equation that models the data. So that is otherwise known as a regression. It is a quadratic regression. And I'm going to go ahead and show you how to do this on Desmos. So I've got my data values typed in right here in the table. And whenever you use your regression, make sure when you type in y and x, you do y1 and then x1. So I'm going to start out with y1. Do not hit equals. It will give you an error if you do equals. So I'm going to hit shift tilde, and then I'm going to do ax1 squared plus bx1 plus c. And at the bottom here, you can see that I rounded to 2 decimal places, 1 and no decimal places. And all you have to do is plug that into standard form. And that just leaves us with the 100-degree water temperature. So the water temperature is your X in this case. So all you got to do is plug that into your formula, and you wind up with 4,967 seconds. Let's go ahead and look at this last question right here. This is something that you can graph very easily using Desmos. And I'm going to pause the video. I'm going to graph it for you real quick. All right, so I've got it typed in exactly as it appears using h of t, and it will graph that. I'm going to try to limit the domain because it says that the domain only exists when t is greater than 0, and it's not doing it. Well, yeah, it is doing it. Technically, it should kind of stop right here, because if you launch this in the air and then it comes back down, this is actually when it's going to hit the ground. It's not going to keep going down into the ground from that. So with that being said, what we can do is we can look at this, and like I just said, it's going to hit the ground at this point. And it looks like it'll hit the ground after about 4 seconds. You can look at how high it's going to go. So at about 2 seconds, it's going to go about 16 feet in the air. So let me just double check and make sure. No, not feet, meters. So it says the rocket hits the ground when t equals 2. No, it actually hits the highest point when t equals 2, or x equals 2 in this case. So A is out, and that means B is in. And we're looking for 2 true statements. It says it reaches a maximum height when your t is 2. Absolutely. So if you go to your maximum up here, the time is 2. So we have found our other answer. That's it. Let me know if you got any questions.